Alrighty, everybody, we just got it okay to start our planetarium show. It's going to be putting away our space trivia questions for now, folks, because now we're going to be heading into the unknown. Ooh. And good afternoon, everybody. Welcome to the Morrison Planetarium. Really quickly, I just want to introduce myself. My name is Christian. I want to be your planetarium presenter. And just a heads up, I'm a person standing right behind you at the very top of the planetarium at the control booth. Hi, good afternoon, everybody. Good to see you. Don't hurt your necks, though. Look forward into the dome before you. Everything that you see in purple is going to be one really big screen, thanks to the help of 6 different projectors heading throughout our planetarium dome. And if you're looking for our projector system, folks, it's hidden just below that purple glow. And also, folks, I'm happy to announce that the show that we're going to watch right now is different from all the other ones that we've done here in the Morrison today. This one's called Tour of the Universe, and this show is completely live, which means that you're going to be hearing my voice for the next 30 minutes. And what this show entails, well, we're going to be starting off pretty close to the Earth, and we're going to be zooming all the way out to the very edge of the observable universe. So hopefully by the end of the show, you won't have an existential crisis of where we are in space, but just a heads up, we're pretty small in the grand scheme of things, so just a forewarning. And before we get started with the show, I do have to go over some quick house rules just so that we're all on the same page and have an enjoyable time. There's a few of us in here this afternoon. First off, folks, there's no food or drinks allowed in. If you manage to bring any snacks, make sure those are put away till the end of the show. We want to keep the theater as clean as possible. We appreciate your help. Also, if you happen to have any cell phones, smartwatches, anything that produces really bright white light or loud sound, now's a good time to put those away for the next 30 minutes, as these can be very distracting and takes away from the planetarium show experience. And folks, if you need to leave early during the show, the exits are always going to be at the very top of the planetarium, so always make your way up the stairs to exit. And the staircase can be quite steep for some folks. If the steepness poses a challenge for you, just remain seated. Once the show's over, we'll have a staff member escort you to a lower exit so you don't have to climb the steep stairs. And last but not least, folks, this show is very immersive thanks to our 75-foot dome above us. If at any point during the show you start to feel overwhelmed, you start to experience motion sensitivity, there's a really quick and easy trick to ground yourself. All you have to do is close your eyes, take in a few big deep breaths, then your brain will remember that you're sitting in a planetarium in San Francisco and not hurtling across the universe, at least not more than the usual. Hee hee. But with that being said, it looks like we're ready to go. So I invite y'all to sit back, relax, and let's begin our tour of the universe. All right, let me regain our controls here. And like I said, folks, we're going to be starting off pretty close to the Earth, not right on it, but we're hovering just above it at this really cool spacecraft called the International Space Station, or the ISS for short. And what's really amazing is that the International Space Station is a research facility. It's a laboratory that orbits around our planet Earth. And they conduct all different types of experiments up here that's a little bit tougher, closer to the ground with much more gravitational influence. Some of the experiments they'll conduct up here are things like what happens when you try to grow plants in space? Do the plants grow the same? Do they grow differently with less gravity? Which way do the roots grow? Another experiment that they conducted up here are things like what happens when you spark a match in space? Does the flame act the same? Does that act differently with less gravity? And one of my favorites is where they had 2 identical twins. One twin lived on Earth for about a year. The other one lived on the International Space Station for a year. After that year, they compared and contrasted the 2 twins. Turns out when you live in space for a long period of time, you tend to age a little bit slower. But not only that, you also lose a lot of muscle because you don't have gravity constantly working down on your muscles all the time. So if you plan to live in space for a long period of time, remember to exercise daily. And folks, the International Space Station looks huge here in our planetarium dome, but it's not that big in actuality. It's only about the size of an American football field. If you've never been to an American football game, that's okay. We could also use the entire California Academy of Sciences, the museum we're sitting in right now. That's about how big it is. And also what's really impressive is that this thing is going incredibly fast. The ISS travels at a whopping 17,000 miles per hour, where it orbits once around the Earth every 90 minutes and experiences 16 sunrises and 16 sunsets a day. Whew, how romantic. And also, folks, this looks really far away from our planet as well, but it's not too far either. The International Space Station is only about 225 miles above the surface of our world. 225 miles, that's nothing for us Californians. That's like going from San Francisco to Santa Barbara, a nice little road trip with the family to get away for the weekend, so not too bad. But to tell you the truth, folks, this is as far as we put humans out into outer space nowadays, only 225 miles above the surface of our world. The reason why is because traveling into space is very expensive, more expensive than living here in San Francisco. And the reason why is because you have to build yourself a rocket ship or buy yourself one. And not only that, you have to account for so much rocket fuel. You need so much rocket fuel, you got to be able to escape the Earth's gravity. And once you accomplish that, you have to account for all the food, water, all the air you're going to be breathing while you're up here in space. So the bill gets quite costly quite rapidly. But folks, the International Space Station is just the first stop in our tour of the universe. So now we're going to see it slowly fade away to the city lights down below. Looks like we're flying just above Europe. I think that's Paris down there. And now we're going to see it slowly fade away. In fact, before we lose track of the International Space Station, I want to add a nice little orbital path so we can see it as it disappears. All right, folks, now we're able to see our entire planet Earth from this viewpoint. And I want to let you know that the space program that we're using here in the Morrison Planetarium is something that you can go home and download if you want to fly through space, just like how I'm doing right now. The space program that I'm using here is called OpenSpace. So if you go to your favorite search engine, type in OpenSpace project, you'll come across the link where you can download this. But just a heads up, OpenSpace isn't finished. It's in its beta phase. So we may come across a few bugs and glitches. If that happens, I'll point them out. Hopefully we can look past that. And then not only that, folks, OpenSpace uses a whole lot of processing power, information. So if you have an older computer, it may overwhelm your older computer. But if you got something new, like a gaming computer, give it a try. It's a whole lot of fun. But if you're a person like me that doesn't want to download anything, you just want to fly through space, well, we also have another great alternative called NASA's Eyes. So just like the human eyeball, type in NASA's Eyes to your favorite search engine, and you can fly through space, and it's so much fun. But in here, we're using OpenSpace. But now that we got a sense of what we're using in here, let's make our way over to our nearest natural neighbor to us in space, the moon. And folks, we humans have been to the moon before. This was between 1969 and 1972, thanks to NASA's 6 Apollo space missions that brought a total of 12 incredibly lucky guys to walk on the surface of the moon. They got to conduct some science up here, and of course they had some fun. Got to play some golf up here as well. But again, last time we sent humans to the moon was 1972, a little more than 50 years ago or so. But don't worry, folks, we humans are making a return trip back to the moon in the next few years, thanks to NASA's new space mission in the works called Artemis. And pretty much with Artemis, we want to be able to, well, first off, we want to come back to the moon and conduct much more science because our science has become much more compactable in size. It's much easier to do more science because our technology has improved. But not only that, we're also going to be sending the first woman to the moon. But not only that, we're also going to be sending the first person of color to the moon. And not even just that, we're also going to be setting up lunar bases throughout our moon. The reason why is because with the Artemis program, we want to send humans deep into space, specifically to Mars. But before we send humans to Mars, we need to figure out exactly how we're going to be living out here in space. So the moon is the perfect stepping stone to figuring out the logistics of how we're going to be doing that because it's much closer to the Earth than Mars is. And not only are we sending those cool folks to the moon, we're also going to again set up lunar bases. And the reason why is because we found ice in the south pole of the moon. And ice is going to be very helpful when you're really far away from home. We can melt that ice, pass electricity through it, then we can separate the hydrogen and the oxygen, and both of that stuff is very valuable when you're way out here in space. So again, we humans should be making a return trip back to the moon in the next few years. Look out for any news about Artemis. Really cool stuff. And folks, sometimes when we're looking at the moon here on planet Earth, the moon sometimes feels incredibly close to us. Feels like you can reach out your arms and touch it. But the moon's incredibly far away. It's about 240,000 miles away from our planet Earth. Whew, 240,000 miles. Some of the adults in this room may have a car with that many miles on it. And if you take better care of your car than I do, you can even imagine driving to the moon if you drove for about 4 months nonstop, going about 80 miles per hour. Although I wouldn't recommend it, the roads out here are poorly maintained. Hee hee hee. And from here on now, folks, we're going to need to use a more useful measuring stick because at this scale, using miles is kind of like using inches to describe the distances between cities because space is so big. So astronomers use a more convenient measurement known as light speed. And light travels at a mind-boggling speed of 187,000 miles per second. That's roughly about 300,000 kilometers per second. So while it took the astronauts more than 3 days to reach the moon, traveling faster and farther than any human has done so since, it only takes light 1.5 seconds to cross that distance at the speed of light. That's kind of like a short pause in conversation. But at last, folks, it's time for us to leave the moon behind. So everybody say bye-bye, moon. See you later. So cute. And now, folks, we're going to see the moon and the Earth in their orbits as they start to slowly fade away, just like how we saw with the International Space Station. And as we saw before, I want to add some nice planet trails so we can keep track of all this stuff while we're out here in space, because, again, space is really big. And not only that, folks, on our journey today, we're going to be traveling much faster than the speed of light. We're going to be traveling at the speed of the human imagination, thanks to the help of computer models like OpenSpace showing us the most accurate images and information available to us. And now the nearest star to us, the sun, should be coming into view on our left-hand side. So here comes the sun. Do-do-do-do-do. And also, folks, our sun is incredibly far away as well. It's about 93 million miles away from our planet Earth. Whew, 93 million miles. That is a good distance away. But in terms of speed of light, that's not too far away. In order for sunlight to travel that distance to Earth, it only takes sunlight about 8.5 minutes at the speed of light. Only 8.5 minutes. That's, again, not too bad. And this is a really cool concept because let's say the sun was to turn off all of a sudden. It's no longer emitting sunlight. That last bit of sunlight will travel that 93 million miles, that 8.5 minutes at the speed of light. Then all of a sudden, the daytime on Earth would become nighttime. So we wouldn't know about it for 8.5 minutes. And this is such a cool concept, folks, because this works for really far away objects as well. Let's say we're looking at a star that's 70 light years away from us. We're looking at that star as it looked like 70 years ago because the light that just reached us took 70 years to get to us. So when you look at really far away objects in space, it's kind of like looking back in time in a sense, which is really, really cool. But now that we have a nice bird's eye view of our solar system, let's do a quick refresher. Right in the middle of our solar system, we have our sun. Closest planet to the sun, we have Mercury. Then we have Venus, Earth, that's us, and then Mars, the red planet. These are the rocky terrestrial planets that we can actually land a spacecraft on, although a couple of them you wouldn't want to because it's really, really hot. And then past Mars, we have our main asteroid belt. This is where you're going to find a majority of asteroids. And there is a whole lot of them. And then past the asteroid belt, we have the really big planets, the gas giants, the Jovians. We've got Jupiter, the largest of them all. Then we have Saturn, famous for its rings. Uranus, the funny one. And then Neptune. These last two ones are the icy gas giants. And then, of course, we can always add everyone's favorite and lovable dwarf planet, Pluto. So here comes the orbit of Pluto on screen. Pluto's just over here on the right-hand side. And a lot of people don't realize that Pluto hangs out here in this outer part of our solar system called the Kuiper Belt. And you're probably wondering, what's the Kuiper Belt? I've never heard of that before. Well, folks, this is the Kuiper Belt. So way out here past the orbit of Neptune, where Pluto is the Kuiper Belt region. And this is like a second asteroid belt way all the way out here in the outer part of our solar system. And what you're mostly going to find out here are icy asteroids and short period comets that don't stray too far away from the sun. And what's really cool is that we kind of came across this in 2006 because in 2006, our telescope and technology greatly improved. So we were able to see much smaller objects much further away. And when that happened, astronomers found more than 400 objects out here in the Kuiper Belt region, and some of this stuff was bigger than Pluto. And we couldn't call all this stuff planets because there was just way too many of them. So all the astronomers across planet Earth had a great big meeting. They had to figure out what exactly you needed to be considered a planet. And they came up with 3 criteria that day, and folks, that was the day in 2006 that Pluto went from being a planet to a dwarf planet. And that's the really cool thing, because as our technology improves, we're able to conduct science and we're able to redefine things and better categorize them. So science is constantly updating and changing, which is such a cool thing. But I'm going to put away the Kuiper Belt because that's just a whole lot to look at. And now I'm going to be adding on screen some many different spacecrafts we sent out in the 1970s to explore our solar system. So now on screen we have the trajectories of Pioneer 10, Pioneer 11, Voyager 1, and Voyager 2. And the latest in law, New Horizons, which flew by Pluto in 2015. Now, all of these spacecrafts are all traveling fast enough to escape the sun's gravity and leave our solar system behind. But even the most distant of these robot adventures, Voyager 1, has not yet traveled as far as light travels in a single day. In order for sunlight to travel all the way out to the orbit of Pluto, it takes sunlight about 5 hours at the speed of light. Only 5 hours to get this far. Not too bad. But now, folks, it's time for us to leave our planetary scale behind us, because now we're going to be heading out into interstellar space, the space between the stars. Distance becomes so immense now, it's going to take us about 4 years at the speed of light just to reach the next star system to us, the Alpha Centauri system. And all the way from out here now, our star becomes one of many stars in our entire star field. And it always takes me a second to find Alpha Centauri, but it looks like it's going to be that bottom right one that we can kind of see close to our solar system. So it's going to be on the bottom right-hand side of our screen. That's Alpha Centauri. We're right in the center. That's our solar system. Again, 4 years at the speed of light just to reach the next star system, folks, to us. But that doesn't put into perspective of how long it would take us humans to travel that distance. Well, folks, if you're getting a rocket ship today of our today's capabilities, make your way over to Alpha Centauri. It's going to take you about 8,500 years to make that trip. And that's just a one-way trip. Whew, I don't think I could live that long. But let's stop and consider whether humanity has made its presence known beyond our solar system, because now, folks, we're going to be stepping inside something called the Radiosphere. And again, folks, we're now inside something called the radiosphere, and this represents the current limits of the most distant radio signals humanity has ever broadcasted, or rather leaked into space. And it extends about 90 light years in all directions, emitting out from the Earth. Now, this first began in the early 1930s with strong radio waves, early television, and radar signal, and then later, the detonation of atomic weapons. All this stuff is emitting electromagnetic radiation strong enough to escape the Earth's ionosphere. And humans were broadcasting well before that. But the earliest radio was not quite powerful enough to escape the Earth. And since these are all these signals are electromagnetic, they're traveling at the speed of light. So this is kind of like humanity's electromagnetic footprint in the universe. And of course, the radiosphere is constantly expanding at the rate of 1 light year per year. So is anybody out there listening? And now, folks, I'm going to be adding some many markers onto the screen. These many markers indicate some many thousands of stars astronomers have discovered over the last 30 years, which has at least one or more planets orbiting around them. We call these planets exoplanets, and we're looking for any of them that are Earth-like with conditions suitable for life as we know it, a place where we humans could possibly live. So far today, we found more than 5,000 confirmed exoplanets just in the nearby vicinity to us, 5,000 other worlds besides our own. And that 5,000 number is going to be increasing as the years continue, because we have spacecrafts where their whole purpose is to find as many exoplanets as possible. So that number is going to be going up. Now, to say if any of them are Earth-like with conditions suitable for life as we know it, well, we cannot answer that question quite yet. But new generations of astronomical instruments are being developed right now and devoted for that specific search. So we've got a little while before we can answer that question. But the more important point here is that quite a few of these planetary systems are within that 90 light year limit of our radiosphere and could have potentially received our signals. However, since radio waves travel at the speed of light, if there is anybody that's out there able to listen in and answer back, the communication delays between hellos could be decades in time. Now, to give you an example, let's say we live in a star system. Let's say this is our solar system on the left-hand side of the radiosphere. We find an alien civilization somewhere on the other side. Let's say this one. We shoot them a text message. We say, hey, we're humans. We live here. Takes 60 years to get to them. They listen in, answer back, another 60 years to get their return message. Folks, that is a 120-year conversation in the making, and I can barely wait for a text message from my friend, so that's going to be pretty tough to communicate with other alien civilizations. But of course, planetary systems beyond the radiosphere, more than 90 light years away, have not heard from us yet, but eventually they will, as the radiosphere is always growing, but it becomes weaker as it does. And I want to be putting away these exoplanet markers for now, but I'm going to leave our radiosphere up on screen because as huge as humanity's electromagnetic footprint is, it is nothing compared to our Milky Way galaxy. So let's zoom on out and get a look at our own galaxy. Alrighty, folks, we're now looking down at our Milky Way galaxy, the galaxy we live in, and I've got to ask, can anybody see their house from here? Just kidding. And folks, our Milky Way galaxy is incredibly large. If you wanted to cross it from one side to the other, it's going to take you about 130,000 years at the speed of light. This thing is huge. And not only that, our Milky Way galaxy is so huge, we estimate that there's at least 300 billion stars in our galaxy. If our recent discovery of so many exoplanets just within our small neighborhood within this vast, massive star city is any indication, there could be billions of planets and potentially millions of Earth-like planets throughout our single galaxy. And before we leave the Milky Way, I want to show you what it looks like from the side. You're going to notice that we live in a big flat spiral disk of the Milky Way plane. And this is important because it kind of looks like a big frisbee or a pancake in space. But when scientists and astronomers want to learn about the universe, it's much easier for them to point their telescopes galactically north and galactically south instead of looking through the plane of the Milky Way, which has planets, stars, gas, debris, things that block their view of the universe. So keep that in mind. We like to point our telescopes galactically north and south. That's going to come important in just a little bit. But folks, the Milky Way galaxy is only one of many hundreds of billions of galaxies that comprise the known universe. So in this giant leap, every single point of light that you're now going to see no longer represents a star, but rather the location of an individual galaxy. Each galaxy containing hundreds of billions, perhaps trillions of stars. And we live in a local galaxy group which contains about 30 galaxies, large and small. Also includes the nearest large spiral to us, the Andromeda galaxy, only 2 million light years away, just next door and heading right for us. We're going to get to know it pretty intimately in about 5 billion years, so mark your calendars. And as our picture continues to expand, folks, you're now going to realize that galaxies are not evenly distributed throughout space. Instead, they like to clump together in large groups and clusters, or they like to avoid each other where there's voids or no galaxies at all. So we can see some nice galaxy clustering towards the center of our screen. We can see some on the very bottom as well. We can see some voids in space towards the top left over here. So you can kind of think of galaxies like people. They like to hang out together or they like to avoid each other. And folks, we've zoomed so far out now that this picture that we're looking at represents the closest 30,000 galaxies to us in a space over 300 million light years across. We got to give thanks to an amazing astronomer by the name of Dr. Brent Tolley, who worked at the University of Hawaii and compiled this amazing representation over decades of time and with other astronomers working aside him. So big shout out to Dr. Brent Tolley. I love flying through this galactic map. But now, folks, we have automated systems that are mapping even the most distant galaxies. So now we're about to see the very large-scale structure of the universe. And remember, folks, every single point of light that you're seeing, that's not a star, that's an individual galaxy. Whew, I feel small. And just to let you know, the large-scale structure of the universe is not in the shape of a bow tie or a butterfly. Remember when I mentioned that we live in a big flat spiral disk of our Milky Way? If we were to line up our Milky Way, it would line up just like so, right down the middle, up and down. And again, we like to point our telescopes galactically north and galactically south. But astronomers still want to make sure that there was galaxies through the plane of our Milky Way. So we have this purple survey right over here. You'll notice that they were still able to find galaxies, just not as many and not as far. Pretty much we have to wait for our technology to improve, and once that happens, we'll be able to map out all these areas that haven't been filled in yet. So it's just a matter of time. And it looks like we're running drastically low on time, so we got to continue on. Because now, folks, we're going to be encountering these really distant, faraway objects known as the quasars. And the quasars are going to be represented by orange dots on either side of the large-scale structure of the universe. So they'll be coming into view in just a second. And the quasars are short for quasi-stellar radio sources. And these blazing objects are all billions of light years away. So now we're looking so far back in the depth of time and space that the most distant quasars represent the universe at a much earlier age. We're nearing the very beginning of galaxy formation. In other words, with the quasars, we're viewing a sort of awkward, gawky teenage version of the universe. And before there was a teenager, there was a baby. So let's press back to a time before quasars, before planets, before stars, and even galaxies began to form. Folks, we're about to see the very edge of the observable universe. And here we are, folks, at the very edge of the observable universe. And what we're looking at is something called the cosmic microwave background image, or the CMB image for short. And all evidence indicates that the universe that we live in is about 13.8 billion years old. And this is data compiled by Planck and other radio telescopes. And the picture that we're looking at is a very baby version of the universe, only 380,000 years after the Big Bang occurred, where space and time began. And this isn't your typical photo either. Instead, what we're looking at is a temperature density image, where the light echoes of the Big Bang are color-coded, where the lighter areas that are kind of in this reddish-orange color are the hottest, least dense regions, and the darker areas are the coolest, densest regions. Now, these fluctuations in temperature and density are extremely tiny. They vary no more than 1 part per 100,000. But these really tiny differences eventually gave rise to that large-scale structure of the universe that we saw moments ago, that clumping and clustering of galaxies everywhere. Figuring out just how that happened is one of the larger challenges for cosmological research today. Though our view here is of the outer edge of the known universe, folks, the earliest light visible to us, that radiation actually persists all around us. It permeates the universe, stretching and cooling as the universe expands over billions of years of time. But folks, we've traveled as far back as the law of physics can physically allow us to go, so we only have one direction left to go. That's going to be back towards planet Earth. So let's find a nice entry point through all these quasars and galaxies. Ooh, this looks like a good spot. And let's make our return trip back to planet Earth, everybody. Alrighty, everybody, we're crossing an expanse of over 13 billion light years. We present you with this view of our universe and the latest in cosmological and astronomical information. We're covering eons and observing objects billions of light years apart. We live in a golden age of astronomy with new generations of telescopes and spacecrafts that are extending the reach of our eyes. And this is all preparing us for the eventual race between the advancement of technology and the accelerating expansion of the universe. And with that thought, everybody, I want to remind you all that astronomy is for everyone. You don't need to be a rocket scientist to enjoy the beauties and wonders of our universe. All you need is the night sky, and if you can, get away from the lights of our cities and look up. Even a good pair of binoculars makes for a decent first telescope, and there's astronomy clubs all around the world that invite people just like you to look through their telescopes and peer into the great beyond, allowing you to partake in the wonders that our universe has to offer. Now, astronomy as a hobby can offer an endless supply of satisfaction, and I do hope you'll join us, those who dream amongst the stars. But it looks like we just made our way back into our Milky Way galaxy. We're heading straight for that radiosphere. And we're making our way back to our neighborhood, our solar system, our star system, in the vastness of space. And now, folks, we're about to pass those spacecrafts we sent out in the 1970s to explore our solar system, passing the orbit of Pluto in the Kuiper Belt region, making our way to the third rock from the sun, our homeworld, planet Earth. All the people that we know, love, ever learned about in history all lived on this one planet. And now we're about to pass the orbit of the moon, the furthest we've ever sent humans out into outer space. And now we're going to be making our final approach back to planet Earth. And folks, if you want to share this show that you just saw right now, you're able to watch this exact show and share it with friends and family on our the Academy's YouTube channel or the Morrison Planetarium's Facebook page. So if you want to share this, you're more than welcome to. But hey, look at that. We made it back home safe and sound, back to planet Earth. And that's the end of our show today. I want to thank y'all for stopping by, and I hope y'all get home safe. Thanks for stopping by, everybody.